Day 462 of doing a LeetCode problem every day until I get a job. All right, y'all, we're back again another day, another LeetCode problem where we're doing daily LeetCode problems. And today we have question number 808, soup servings. The difficulty level is medium, but don't worry because you already know we're going to keep the solution as simple and easy to understand as possible. But before we get started, y'all, don't forget to like, comment, subscribe, and share. And if you need any new Apple AirPods, go ahead and check out that link in the description so you can get you some. Now let's see what the question says. You have two soups, A and B, each starting with N milliliters. On every turn, one of the following four serving operations is chosen at random, each with the probability of 0.25 independent of all previous turns, so a 25% probability. Pour out 100 milliliters from type A and 0 milliliters from type B. Pour out 75 milliliters from type A and 25 milliliters from type B. Pour out 50 milliliters from type A and 50 milliliters from type B, or pour out 25 milliliters from type A and 75 milliliters from type B. Note, there is no operation that pours out 0 milliliters from A and 100 milliliters from B. The amounts from A and B are poured simultaneously during the turn. If an operation asks you to pour more than you have left of a soup, pour all that remains in that soup. The process stops immediately after any turn in which one of the soups is used up. Says return the probability that A is used up before B plus half the probability that both soups are used up in the same turn. Answers within 10 to the negative fifth power of the actual answer will be accepted. All right, y'all. So now that we've read the problem, I understand how that may be a lot to take in. So let's go ahead and take a look at these examples so we can make sure that we are doing this problem correctly. Now, the first thing we need to understand is that when we're dealing with probabilities, the probability is going to be from 0 to 1, right? That's how probabilities works. That's just how math works, right? 1 is 100% probability, 0 is a 0% probability. And this right here, answers return within 10 to the negative power, or excuse me, 10 to the negative fifth power. That just means like an answer, like say, like I said, 1 is the highest, right? So say our answer is 1 point, or excuse me, not 1 point, but 0.99999. If we put a 1 for that, that will be accepted because this right here falls into the within the 10 to the negative fifth power of 1. So that's all that means. Now, let's take a look at these examples. So the first thing I'm going to do is I'm going to copy and paste the decision tree just so you can get a visual representation of what's going on. So this right here is example 1. So in example 1, we have our input n equals 50. Our output is 0.625. Explanation says if we perform either of the first two servings operations, soup A will become empty first. If we perform the third operation, A and B will become empty at the same time. If we perform the fourth operation, B will become empty first. So the total probability of A becoming empty first plus half of the probability that A and B become empty at the same time is 0.025, which comes from this right here, right? Because there's four different options that we can choose from. Each of them has a 0.25 chance of occurring, and then we multiply that by 1 plus 1 plus 0.5 plus 0, and that's going to equal 0.625. So let's break that down with this decision tree so you can actually see how the math is math and how the math works. So we have our input n that equals 50, right? So these right here, this represents our four measurements that we will be pouring out. So the first measurement, we can pour out 100 from A and 0 from B. That's this right here. Pour 100 milliliters from A and 0 milliliters from B. That's what this represents, this 100 and this 0. This 75 and this 25 represents our second operation or possible operation. Pour 75 milliliters from A and 25 milliliters from B. That's 75 from A, 25 from B right here. Then our third possibility, pour 50 milliliters from A and 50 milliliters from B. That's represented right here with 50 and 50. And then finally, pour 25 milliliters from A and 75 milliliters from B. That's represented right here. Pour 25 from A, 75 from B. So N is equal to 50, right? So if we want to find the probability that A is used up before B, right? So if N equals 50 and we pour 100 from A and we pour a 0 from B, that means A will get the 0 and B will stay at 50. So that means it has a probability of 1, or it's 100% that A will be empty before B, because we poured 100 from A and we only start with 50. We're only starting with 50. If we pour 100, we would be in negative 50, but we're stopping at 0. So we pour out this whole 50 milliliters just off this first possibility, or this first turn right here, because if there's only 50, we poured out 100. So it would be 0 for A. A would be empty. B would still be at 50 because we're pouring out 0 milliliters from 50. We're starting at 50 and we're pouring out 0 milliliters from B. So B would stay at 50. And since A is at 0, B is still at 50, that means A ran out first. So the probability would be 1, or 100% that A would run out first. Similarly with this right here, if we pour out 75 and we only have 50, then A is going to be 0. There's going to be nothing left in A because we were able to pour out 75 milliliters, but we only had 50 to pour out. So once again, A would be empty. And if we poured out the 25 from B, right, because it says pour out 75 from A and 25 from B. So if we poured out the 25 from B, B would now be at 25. However, that's not empty, right? Because we started at 50. So 50 minus 25 is going to equal 25. So A would be empty, B would be at 25. So this also has a probability of 1 that A would empty first, because there's only because there's only 50 milliliters to pour, and we poured out 75 from A. So A will empty first in this one as well, in this probability branch or tree right here. Then come over here, if we pour out, this is the third serving operation, where we pour out 50 from A and 50 from B. So this would bring both of them to 0 because we're only at 0. So we would pour out 50 from A, that'll give us the 0, A would be empty. Then we pour out 50 from B, that will get us to 0, and B would be empty. So since they both become empty, that gives us a 0.5% chance, or 50% chance that A would become empty before B, because they both end up being they both end up being empty. So there's a 50% chance that A will be empty before B. So that's a 0.5 right here. Then finally right here, with this serving operation, if we pour out 25 milliliters from A, then we'll still have 25 milliliters left. But if we pour out, because we're starting from 50, but if we pour 75 milliliters out from B and we only have 50, then that means B will be empty and A will not be empty. So this means A has a 0% chance, because remember, we're worried about A being used up first. So this right here, this tree, A has a 0 possibility of being empty before B, because B poured out 75 and there was only 50, and A only poured out 25 out of the 50. So B is going to be empty first. So A has a 0% chance of becoming empty first. So now that we have these possibilities right here, or these probabilities right here, we add them all together. So if we add all of these together, we will get 1 plus 1 plus 0.5 plus 0. That's going to get us 2.5. But we need to divide it by 4. So remember, there's 4 different possibilities, so we're going to divide it by 4. So 2.5 divided by 4 is going to get us 0.625, which, as you can see, is our output. And that's how we got our output, y'all. Just like that. It was that simple. Wasn't that hard. So let's go ahead and take a look at example 2. Example 2 is a little bit more tricky. It's the same principles though. So in example 2, we have our input n equals 100. This time our output is 0.71875. Explanation says if we perform the first serving operation, soup A will become empty first. If we perform the second serving operation, A will become empty on performing the operation 1, 2, and 3, and both A and B become empty on performing operation 4. If we perform the third operation, A will become empty on performing operation 1 and 2, and both A and B become empty on performing operation 3. If we perform the fourth operation, A becomes empty on performing operation 1, and both A and B become empty on performing operation 2. So the total probability of A becoming empty first plus half of the probability that A and B become empty at the same time is 0.71875. So let's look at this decision tree once again so we can see how they got that. So we have our input n that equals 100, right? Boom. So once again, these are the probabilities of each, or these are the serving operations of each. These are the serving operations, right, of A and B. So once again, we pour out 100 from A. If we pour out 100 from A, we're starting at 100, so we pour out 100 from A. A becomes 0, that means A is empty. B, we pour out 0 from B, so B stays at 100. Then we do the same thing for the second operation. So if we pour out 75 milliliters from 100 for A, then we'll be left with 25 for A, and we pour out 25 milliliters from 100 for B, then that means B will be left with 75 milliliters. When we do the third operation, 50 and 50, we pour out 50 milliliters for A, that leaves A with 50, pour out 50 milliliters for B, that leaves B with 50. Boom. Then for finally, last but not least, we pour out 25 milliliters from A. That's going to give us 75. Then we pour out 75 milliliters for B. That's going to leave us with 25. Now, we're not done yet, right? Because as you can see, this is not empty, right? For the second pouring out operation, we would have to do it again. So this is not, this is not empty yet. So we would just have to do it again. So let me just come down here so y'all can see. If we pour out, if we're looking at this tree or this branch right here, so, and now this 75 and 25, or excuse me, for there's 25 milliliters left in A and there's 75 milliliters left in B. So if we perform these operations again on this right here, we pour out 100 from A and 0 from B. So now A would be 0 because A only has 25 and we poured out 100. So A becomes 0 and B will stay at 75 because we're pouring out 0 from B, right? So boom. So now that's just 1. So that gives us a probability that 1 will empty first. Then we have to perform this operation, right? So let's just come over here for the second operation. We pour out 75 milliliters from A. A once again is 0. There's nothing left because it only started with 25. And B will become 50 because we poured out 25 from this 75. Boom. So B becomes 50. Once again, A finishes first. So the probability is 1 that A is going to finish first. Then we come right here and we do it again. So we take 50 from 50, that's going to be 0. That's going to be 0. We take 50 from this 0. So once again, now this is 0. And now take 50 from this is 0. And this is going to be 0. Boom. And now we are, or excuse me, no, I'm looking at it wrong. Sorry, y'all. We're taking 50 from this 25, not this 50. Sorry, we're taking 50 because we're looking at this right here. We have to do this one over. So we take 50 from 25. Once again, A is empty. Then we take 50 from 75, and then B will be left with 25. Boom. So once again, A empties first. Boom. So the probability of A emptying first is 1. Then we come over here, and now we take, or we right here, sorry. So we would, this operation, we take 25 from 25, so A would be 0. And then we take 75, this 75, because remember, these are just these operations. So we take, when we perform this operation, we're going to take 25 or 25 over here from A, and A only has 25, so now A is 0. Then we come over here and we take 75 right here. We take 75 from B, and B is already 75, so 75 will be 0 as well. So once again, if they both empty out 0, 0, then that's a 0.5 or 50% chance. Boom. So then when we add all these together, 1 plus 1 plus 1, that's going to get us 1 plus 1 plus 1 plus 0.5, that's going to get us 3.5. We divide that by 4, and that's going to leave us with 0.875. That's how we got this 0.875 here. So let me get rid of this. Boom. Because that's just when we did this one over. Then we come right here, it's 50-50. We already know from before that that's going to get us 6.25. So this becomes 6.25. And then this, you can do the math on your own, similar to homework. Do some homework. This is some homework for y'all. Do this one on your own, just like we did this one, but it should come up to 0.375. Then once we have all of these probabilities, once again, we take all 4 of those probabilities, we add them together, then we divide them by 4. That's going to get us 2.875 divided by 4. And then when we divide 2.875 by 4, that's going to get us 0.71875, which is our output, and that's how we got it. So I hope that made sense to y'all. And now that we understand the question, let's get into the fun part, the actual solution. So let me get rid of that real quick while we get into this solution. Now, first thing we're going to do, we're going to create a recursive helper function. We'll call it F, and this is going to represent the probability that soup A will be empty first. So for that, we could just declare or create another function. We could call it F. We're going to open up the parentheses. We're going to say underscore A colon. That's going to be an integer, comma, underscore B colon. That's going to be an integer. And then we're going to come outside of that and we're going to return a double. Boom. Now we need to create a base case for if both soups empty at the same time. That means our probability will be 50% or 0.5 like we discussed earlier. So we're going to handle that and say if A is less than or equal to 0 and 2 and signs, B is less than or equal to 0, then we can just open up the brackets and we can say return 0.5. Boom. Now we need a base case. If soup A is empty first, then the probability is 1, like we discussed earlier. So we're going to say if A is less than or equal to 0, then we could just open up the brackets and we could return 1. Then we could come right here underneath this, and we're going to handle the base case for B. If B empty first, then that means the probability was 0 that A will be empty first, like we discussed before. So we're going to say if B is less than or equal to 0, then we could just return 0.0. Sorry, because we're working with doubles. So now if we have already computed this state, then we can return the cache result. So we're going to come right here. We're going to say if let C equals cache square bracket A comma B. Then we come outside of this, open up the brackets, and we can say return C. Boom. Now we're going to use our recursive transitions. Each of the 4 serving options is equally likely probability of that each of the serving options is equally likely to occur with a probability of 0.25. So for this, we're going to say, we're going to come underneath this, and we're going to say let ands equal 0.25 times, then we're going to open up the parentheses. Boom. And then, so if we serve 100 milliliters from A and 0 from B, then that's going to be F, open up the parentheses, A minus 100, comma B. Come outside of that, we're going to say plus, and then we're going to come underneath that. If we serve 75 milliliters from A and 25 milliliters from B, we're going to say F, open up the parentheses, A minus 75, comma B minus 25, come right here, come outside of that, say plus. Then if we serve 50 milliliters from A and 50 milliliters from B, we're going to say F, open up the parentheses, A minus 50, comma B minus 50, come outside of that, we're going to say plus. Then finally, if we serve 25 milliliters from A and 75 milliliters from B, we're going to say F, open up the parentheses, A minus 25, comma B minus 75, just like that. And we need to store the result in our cache, so we're going to come right here underneath the parentheses or outside of the parentheses, and we're going to say cache, open up the square brackets, A comma B, or excuse me, it should be two square brackets, square bracket, A comma B, and we're going to come outside of that, and we'll say equals ands. Boom, then we could just come underneath that and say return ands, just like that. Now for optimization, for large data sets, the probability or data sets where n is greater than 5,000, the probability approaches 1 due to high likelihood of soup A emptying first. So we're going to handle that by coming underneath this, and we're going to say guard n is less than 5,000, else we could just return 1. Boom. Not done yet, but we're getting there. We're going to map the state of A and B or to the probability. So we're going to come underneath this, declare a variable called cache, and we're going to set that equal to the array of integers, and that, or excuse me, not to the array of integers, it's going to be a dictionary with the integer, then a colon and a double, like that. Come outside of the square brackets and put the parentheses. Boom. Now we need to initialize our call and start from our full servings and simulate the first serving by coming underneath this. We're going to say return 0.25 times, open up the parentheses again, and once again we're going to say F, open up the parentheses, n minus 100, comma n, come outside of that, we're going to say plus, then we're going to say F, open up the parentheses, n minus 75, comma n minus 25 for the second serving operation. Come outside of that, say plus. Then for the third serving operation, we're going to say F, open up the parentheses, n minus 50, comma n minus 50. Come outside of that, put plus. Then for the last serving operation, we're going to say n minus 25, comma n minus 75. Boom. That should be all she wrote. Wasn't that much code, y'all. So let's go ahead and run it. Make sure it runs properly before we submit it. Okay, let's see where that error is. Okay, so cannot find cache and scope. Now, hold on, y'all. Let me see. where, let me see. Oh, sorry, y'all. Should be like that. It's a little typo. Let's run it again. And it's accepted, so let's go ahead and submit it. Make sure it's still accepted after we submit it. And look at that, y'all. 3 milliseconds beats 100% of users. That's what I'm talking about. That's what I like to see. So before we go, make sure y'all get one more look at the code. This is the top part. This is the bottom part. And yeah, y'all, with that being said, I hope y'all learned something today, and I hope to see y'all here tomorrow for another day, another LeetCode problem. See y'all then.